have pivots, so x and z are sort of fixed. There's no pivot in the column for y, so you'd say let y be equal to alpha, or let y be equal to s, or some other parameter which you're allowed to be an arbitrarily real number, right? So that's the important thing that you've got to remember here. If you have more columns than pivots, you must introduce 3 variables. So you've got 3 or 4 minutes. Go ahead, and then after we've solved these, we'll move on to the next section of work.
What exactly do you mean by a pivot?
So the pivots are they're the leftmost non-zero entry. Okay, so there's one at the back there, and there's another one right at the back. Once again, is anyone sitting next to an empty seat? Anyone sitting next to an empty seat? Okay, so there's one over there. Just maybe would everyone in that row shift up? In fact, yeah, it's easier to come around from this side. Okay. All right, so let's talk about the solutions here. So I already sort of told you what's going to happen for this first case. We've got x, y, z, and we don't have a pivot in the second column. So the second column, y, is going to be equal to alpha. So we've got something like y is equal to alpha, and then you just read off the rest of the answer. So there's always a constant vector. In this case, because we are in the homogeneous case, I think we're out of seats. In this case, because it's the homogeneous case, your constant vector here is just zeros. And if you read that first row, you get x plus y is equal to 0. And we said that's really x plus alpha is equal to 0, so that's x is equal to minus alpha. So x is equal to minus alpha. All right. Now we take a look at the next one, number 2. We have, again, 3 columns, x, y, z, and we only have one pivot. Yes? Okay, so what we do is we look at this row, say, or in this case, this row and this row. Those are rows which don't have pivots in them. Okay, so here you would say, let y be equal to alpha. Here you would say, let y be equal to alpha, let z be equal to beta. Every row without a pivot, you've got to let the corresponding variable be free variable. So you allow it to be something alpha, beta, whatever you want to call it, right? And now if you read off that top row on the left, it says there x plus y, which is really x plus alpha. So it says x plus alpha is equal to 0, which means that x must be minus alpha, which is what we've written down here. X is equal to minus alpha. So we do something similar over here. Because we've got 2 free variables, we know immediately that our solution must have the following form. It must be some constant vector plus alpha times by some vector plus beta times by a second vector. 2 free variables, so we must be adding 2 vectors like this. And we said that y was equal to alpha and z was equal to beta, so you can fill those in over there. So y is equal to alpha, so it must be 0 plus alpha and no betas, and z must be 0 plus no alphas plus 1 beta. So all that's left is to think about x, and that first line says x plus alpha is equal to 4. So x is equal to 4 minus alpha. X is equal to 4 minus alpha and no betas. And that will be our solution. All right. For the third, for that third system, yes? What do the free variables do? The free variables are just allowed to take any value from R, right? So they're just some real numbers. They're sort of some parameters that we use. And we say, as we allow alpha to change, how does our solution change? And you can see that over here, as alpha changes, our solution is sort of describing a straight line. And over here, as we allow alpha and beta to change, our solution space is it's some sort of plane. Right. So if we look at number 3, if we look at the second row of number 3, the second row of number 3 is saying 0 times by x plus 0 times by y plus 0 times by z is equal to 4, right? And that's impossible. So there are no solutions over here. So you just write something down like inconsistent. Or if you don't want to write inconsistent, you could write down something like no solutions. But the point is, there's no solution for us to write down over here, because we've got, I'll be with you in a moment, we've got 0x plus 0y plus 0z is equal to 4 is, it's impossible for us to have that. Yes? Why is over here? Why is there this one here? Okay, well, there's that one over there, because if you look at what I've written underneath that third column, I've said that z must be equal to beta, right? So now if I read the bottom row over here, I've got z is equal to 0 plus 0 alpha, and it must be a 1 over here because z is supposed to be equal to beta, right? So there must be 1 beta. All right. Yes? Why do we could ignore that second row for question 2, because it's a row of all zeros. No, you would get z is equal to beta because you would still have 3 columns, and there still wouldn't be a pivot in the second or third column. So adding or removing rows here, I mean, if I just add a row of zeros to this equation, I guess this is the only one we haven't done yet, right? If I just add a row of zeros, that doesn't change how many of those columns I have. I still have 5 columns. I've just added an extra row of zeros. And it also doesn't change which of the rows have pivots in them, right? I mean, the rows that had pivots still have pivots, and the rows that don't have pivots still don't have pivots. So these rows of zeros at the bottom effectively make no difference to the solution. Right. So the last one, we've got 1, 2, 3, 4, 5 columns, so that we know our solutions are going to be a vector x1, x2, x3, x4, x5. And if we look at this, we've got 3 rows, and the first and the second and the fourth columns have pivots, which means that over here, x3, that's going to be equal to alpha, and here, x5, that's going to be equal to beta. But we've got some free variables. Right, so what do we say? We said x3 is equal to alpha. So x3 is this 0, alpha, and no betas. And x5 we said was beta. So we can write that down immediately. And now we just have to think about x1, x2, and x4. So what is x1? Well, the very first row says that x1, 1 times by x1, plus 3 times by alpha is equal to 5. So that's really just saying that x1 is equal to 5 minus 3 alpha. So this first row should be 5 minus 3 alpha. So 5 minus 3 alpha, and there were no betas. x2, we'll take a look at the second row. So we get x2 minus 2 alpha plus 4 beta is equal to 0. So x2 is equal to 2 alpha minus 4 beta. So it's a 0, 2 alpha minus 4 beta. And then that last row, the last row is saying, okay, 0, x1, 0, x2, 0, x3. Okay. So it's saying x4 plus beta is equal to 2. So that's x4 is equal to 2 minus beta. So x4 is equal to 2 minus beta. Again, there's a 0 over there. And so we've written down solutions for these augmented matrices. Is everyone happy with this? Yeah. Okay, so we're going to move on now to the next section, which is generating sets. And we'll start with a definition. Wait, sorry, I'm doing definitions in green. We'll start with the definition. So we have 2 subsets of a vector space. S and T are both subsets in this vector space. We write down this over here, S with these sort of angular brackets. This means the new set, which is a linear combination. It's all the possible linear combinations of elements of S. So this over here is the set of all possible linear combinations of vectors of S, right? So these angle brackets mean, just say that you take all the possible linear combinations of all the things that were in S, and you bundle them up together. And if this set of all the possible linear combinations is equal to T, so if this set here is equal to T, then the sort of wording that we're going to use is we're going to say either we can say that S generates T, or we can say that T is generated by S. Either of those, I mean, those are equivalent. So if the set of all linear combinations of vectors in S is equal to the set T, then S generates T, or T is generated by. Okay. And I guess we can maybe maybe just do some examples. As we go through these examples, we can maybe get a better sense of what it means to say that one set generates another. Okay, so here's the first example. And I guess we can actually do a whole bunch of examples. So I want to know what sets are generated by. Okay, so question 1. What is the set which is generated by just this vector 1, 2? And then second question, what is the set which is generated by this set 1, 2, 3, 6? And the third question, what is the set generated by 1, 2, 1, 0? And I guess I'm going to want to talk about these sets a little bit later on, so maybe we should give them names. Call this set A, B, and C, right? So what are the sets generated by A? What set is generated by A, what set is generated by B, and what set is generated by C? And you've got, again, a couple of minutes to think about this, and then I'll start talking through it. Okay, so settle down. So we have the set A over here, which is just a set with one vector in it. It's the set with the vector 1, 2 in it. what is the set generated by A? And before we write something down, just geometrically, can anyone tell me what is the set which is going to be generated by A? It's a line, right? It's going to be a straight line through the origin, passing through the point 1, 2. So if we write it down like this, we'll have alpha 1, 2. Alpha is some real number. And this is just a line, right? So this is a line that's a line through the origin, right? What about B? What is the set generated by B? It's the same line, right? It turns out to be the same line because this is alpha times by 1, 2 plus beta times by 3, 6. Alpha and beta are real numbers, but what we might notice is that 3, 6 and 1, 2 are just multiples, right? So you could rewrite this. Let's maybe just write down a couple of lines here until we convince ourselves of this fact. This is alpha 1, 2 plus 3 times by beta 1, 2. Alpha, beta, elements of the reals, right? And this is really alpha plus 3 beta 1, 2. Okay, so I mean, this is just some real number multiplied by 1, 2. If you want to, you could rename this, call this gamma. Yeah, maybe we should just rename it, call this gamma. But we just have a scalar multiple of 1, 2. Okay, so it turns out that the set generated by A and the set generated by B are exactly the same, even though A and B are different. So this is true, right? The set which is generated by A is the same as the set which is generated by B, even though A and B are different sets. Okay, they both generate the same straight line through the origin. And then the third problem we've got this set C over here. Let's just go back and take a look at C. So what is the set which is generated by C? It's R2. It's all of R2. And let's think about that a little bit, right? So this is alpha 2, 1. Oh, sorry, 1, 2. 1, 2, right? Yeah, alpha 1, 2. Plus beta 1, 0. And someone said, though maybe it's not immediately obvious why, that this is all of R2. So why is this all of R2? Who said that it was all of R2? Yeah, why is it all of R2? Why? They're in different directions. Okay, so we're getting sort of to the crux of the matter. Because this is an R2, we can sort of see that geometrically very easily, right? But it might be a more difficult thing to do if we were working with, say, 5 vectors in R5. Then how do you know if those 5 vectors in R5 are pointing, in some sense, all in the same direction, or if they all lie in the same hyperplane? Yes? Yes, in R2, but things become a little bit more complicated in higher dimensions, right? Because, for example, just in R3, you could have 3 vectors, none of them are scalar multiples of each other, but they might all lie in the same plane, which means that the set that they generate will not be all of R3, it'll just be a plane, right? So it's, in R2, yes, it's very easy, but let me just show you a method for deciding whether or not this generates the whole of the space, which is going to be generalizable to R3, R4, Rk. And so we would write down something like this. We want to know if we can reach an arbitrary vector xy So can we find so we want to know if we can write down any vector xy in the following way. We want to write down xy is equal to alpha times by 1, 2 plus beta times by 1, 0. And if we think about this, this is really a system of equations that we're trying to solve. We're trying to find values for alpha and beta that will make this true. And how do we solve systems of linear equations? Well, we can solve them by doing some Gauss reduction. So we write up an augmented matrix. And we have an augmented matrix over here, which is just going to be, so the first column corresponds to alpha, the second column corresponds to beta, and then we want xy, we want a combination of 1, 2, and 1, 0 to add up to give us xy. So we write down an augmented matrix like this, and you can try to Gauss reduce that a little bit and see if you can get values for alpha and beta. Well, you should be able to get values for alpha and beta. So do the Gauss reduction, and once you've done that, we'll think about what that actually means. is equal to alpha 1, 2 plus beta 1, 0. We formed an augmented matrix, right? So each column in that augmented matrix, the first column corresponds to alpha, the second column corresponds to beta. And now we've done our Gauss reduction. So you can see the first thing that we've done is we've identified this over here as a pivot. I guess maybe I can circle it in pink like I've done previously, right? So we identified that that's a pivot. So we're going to try to make the entries underneath it 0. So we've got to subtract 2 times the first row minus, so the second row minus 2 times the first row. So we've made this entry 0. And then we get the rest of the entries in the second row. And then we identify this as going to be our next pivot, right? So we've got to rescale it so that it's got a value of 1, which is what we've done. We've just multiplied it by negative 1/2. Negative 1/2 times by negative 2 gives us this 1. And now we make the entries above the pivot. Make these entries 0. So we just have to take row 1 and we replace row 1 with row 1 minus row 2. Okay, so we do the Gauss reduction and we get this far. And this is nice. If you do a Gauss reduction where the number of pivots and the number of columns is exactly the same, then there's one unique solution. And we can write down the solution very easily. We just have alpha is equal to 1/2 of y, and beta is equal to x minus 1/2 of y. Right? So what that's saying is that if you want to write down x, y as a linear combination of these two vectors, you can do it, right? So we said alpha will just be a 1/2 y times by 1, 2 plus beta x minus a 1/2 y times by 1, 0. So if we just choose a vector in R2, so for example, give me a real number, 2, and another real number. There were lots of ones. The first one I heard was 7, right? So if we want to write down 2, 7, we would just write this down as, okay, so it'll be a 1/2 of y. So that's 3.5 times by 1, 2, plus, now it should be x minus a 1/2 of y. So x is 2, 2 minus a 1/2 of y. So 2 minus 3.5 is actually negative 1.5. And you can see that this works, right? If you look at the x component, you get 2 is equal to 3.5 minus 1.5, which is true. And the y component is 7 is equal to 3.5 times by 2 minus 0. Okay, all right. So we can now write any vector we like in R2 as a linear combination of these two vectors. So really it is the case that these two vectors do span R2. I mean, we sort of saw that geometrically, but this is something that we can use when we're working in R3 or R4 or some higher dimensional space where it's maybe not quite as easy to visualize exactly how this works. All right. Any questions about this? Okay, well then let's keep going. We are now at fact I think we're on 1.16. Fact 1.16 is the following. I can take any subset of a vector space. Yes. Oh, you're just stretching. Oh, yeah.
Isn't that just isn't that symbol the S is a subspace on the
No, this is the subset symbol. We said that a subspace is a subset, but then it's got to also satisfy some additional conditions. And those additional conditions were that it's a subset which is closed under vector addition and closed under scalar multiplication. Right? So this symbol here is just the subset symbol. Yes? Is there a symbol for a subspace? Yes, there is a symbol for a subspace. I'm not actually sure. I think it'll be something like that, which is some odd looking shape. But I don't know that we'll ever use it. All right. So if we have some subset, which is in our vector space, right? For any set, any subset inside our vector space, any subset in our vector space generates a subspace. Okay. You start with a subset, you think about what does the subset generate? Generates something, and that something is a subspace. So that's what we're going to try to show now. So I think what I'll do is I'll start writing and maybe leave some gaps for you to fill in. Right. So what we know is the following, right? So S is contained in V, right? S is equal to, let's just call it V1, V2, up to Vn. I mean, actually, strictly speaking, maybe we should just say ... It might be an infinite subset. It might be an infinite subset. It's not clear that there will be an nth element. So we take here S is equal to V1 all the way up to V2, V3, V4, and maybe it stops at Vn, or maybe there are an infinite number of things in this set. What we're going to do now is we're going to think about two arbitrary elements of the set generated by S. So call these vectors, okay, let's not call them U and V, since we've already used V over there. Let's call them P and Q. Right, so let P and Q P and Q be elements of the set which is generated by S. So if P and Q are sets which, if P and Q are elements of this set which is generated by S, we could write P and Q in the following way. P is going to be a linear combination of V1, V2, and so on. Right, so a linear combination, we can just write it as a sum of alpha i's times by vi's. Right, and this will be for we'll just sum over whichever ones go into making up P. P can't be an infinite sum of these vectors, so some of these, it might be that P is equal to 3 times by V1 plus 5 times by V2 plus 0 times by V3 plus 0 times by V4 minus V5. So we're just going to have a sum over possibly some of the vectors, right? Not necessarily all of the vectors. So P is a linear combination of things from our set S. And similarly, Q is also going to be a sum let's call these beta j's bj. Right. Yes.
So you're saying that S is a subset of B.
S is a subset of B, yes.
But then if you do a linear combination of only some of the elements in S, then can you really say that linear combination can generate a subspace if you're not using the whole of this?
Okay, so what we're talking about, in this particular case, we're looking at P is one particular linear combination of things in S, and Q is one particular linear combination of things in S. But we've taken P and Q as arbitrary elements of the set of all possible linear combinations. So this over here is going to have an infinite number of things in it. So it's going to be all the possible linear combinations that we could create using the elements of S as our building blocks, right? We're just looking at two particular cases, but I mean, these could be any of the infinite number of linear combinations. All right. Any other questions at this stage? No. So what we need to do now is we need to check, okay, sorry, this should be Q with a little dash since it's a vector. what we need to do now is we need to check that if we take P and we take Q, right, so two vectors in this set over here, if we add them together, then we should recover something which is still in that set, right? Because that would be closure under vector addition. So what we want to do now is we want to write down, so we want to check if P plus Q is still in the set of all the possible linear combinations. Okay, so does anyone have any thoughts about why this might be true? Any suggestions for what we do? Yeah?
If you are only sum of the linear combinations, then the sum of them would be another linear combination.
Exactly, right. I mean, so P, we're just adding up a bunch of vectors, and all those vectors were in the set S. And Q, we're just adding up a bunch of vectors, and all those vectors were also in that set S. So now when we add up these two linear combinations, we're still just doing addition, right? We're not suddenly introducing some new operation. So P plus Q, is just going to be this sum over here. Let's just say we're going to sum over some i's, alpha I, vi, plus the sum of the sum j's, like that. And we can rewrite this in the following way. We can rewrite this as the sum of a sum k's with a new coefficients, gamma k. And gamma k is either alpha, let's say alpha k, beta k, or alpha k plus beta k if vk was in the first sum. So this is a really, I guess, only the tricky part. You've got to think a little bit carefully about what your coefficients are going to be. You've got to think a little bit carefully about what these coefficients should be. So we're adding up a whole bunch of vectors. These vectors vi all come from S. And these vectors vj also all come from S. Right? But there's no guarantee that they're... I mean, so that first vector p might be adding up, say, v1 plus v3 plus v5 plus v7 and so on. And that second sum might be v2s and v4s and v6s and v8s. So there's no guarantee that there's any overlap between them. On the other hand, there may be overlap between them, right? So these coefficients here, if a vector appears only in that first sum, then you just take the coefficient from the first sum. If the vector appears only in the second sum, then you take the coefficient from the second sum. If the vector appears in both sums, then you just add those two coefficients. You just take a new coefficient, gamma k will be alpha k plus beta k. But the point is, this is now just a linear combination, right? These are just some coefficients, and we have to think a little bit about how we choose those coefficients. These are just some coefficients, and all of these over here are elements in S, and they're all elements in S because these over here were elements in S, right? So this is a linear combination. This is a linear combination of vectors in S, which implies that the set generated by S is closed under vector addition, right? And what we still have to do, and you can do yourself, so check yourself, check for yourself that the set generated by S closed under scalar multiplication, and really it's very obvious what's going to happen here. You write down your vector P, and P is just going to be, some alpha I vi, and then you multiply that by some scalar C, and all that happens is you change your coefficients from alpha I to C alpha I, and it still looks like a linear combination. And so we get closure under scalar multiplication as well, which means that we have that the set generated by S is a subspace. Okay, so there's a tut today, otherwise I'll see you, I guess, tomorrow.